Okay, so picture this, a single scientist whose work is the foundation for two completely opposite things. I'm talking about the unbelievable fire of the atomic bomb and the absolute freezing cold that makes our super precise digital world even possible. That scientist? Enrico Fermi. And today, we're diving deep into his incredible story.
So the big question is, right? How on earth did one guy become the architect of two such different worlds? Well, let's get into it. First thing you need to know about Fermi is that he was, well, to put it lightly, a total unicorn in the world of physics. Seriously. His peers just called him the master of everything. And this quote here from C.P. Snow, it says it all. This isn't just, a nice compliment. Snow is basically saying that if Fermi had just been born a little bit earlier, he probably would have discovered the atomic nucleus and developed Bohr's theory of the atom, all by himself. That's how big of a deal he was. It's the kind of talent that comes around once in a century, if you're lucky. And here's what made him so incredibly rare. See, in physics, you usually get two types of geniuses. You've got your theorists, the Einsteins, right? The people who dream up the universe on a chalkboard. Then you've got your experimentalists, the folks who get their hands dirty building the massive machines to actually test those theories. Finding someone who was world-class at both, it's almost unheard of, but that was Fermi. He could cook up these deep quantum theories and then just walk down to the lab and build the gear to prove them. All right, so let's look at how this incredible talent actually played out. His first huge contribution, it wasn't some machine, it wasn't a bomb. It was a set of rules, the actual rules that govern the very fabric of matter itself. He literally gave his name to a whole family of particles, fermions. You're made of them, I'm made of them. Protons, neutrons, electrons, they're all fermions. And the key thing to know about them is that they're, well, kind of antisocial. They follow something called the Pauli exclusion principle, which is just a fancy way of saying that no two fermions can be in the exact same quantum state at the same time. Think of it like a movie theater with assigned seating. Once a seat's taken, you can't sit there. That simple rule? It's why matter is stable. It's why the floor you're standing on is solid. It's one of the most basic, fundamental rules of, well, everything. And this wasn't just him scribbling on a blackboard either. This picture shows him in Rome back in the 30s with his amazing research team, the Via Panisperna boys. These were the guys in the trenches, running the groundbreaking experiments that started to crack open the secrets of the atom. And that work, well, it was about to change the entire world. And that, of course, brings us to the first world that Fermi helped build, the world of nuclear fire. All that theory was about to become very, very real. And just look at how fast everything happened. It's just mind-boggling. In 1938, he wins the Nobel Prize, but he has to use that trip to escape fascist Italy because his wife was Jewish. He gets to the US in 1939, right as the news of nuclear fission is spreading like wildfire through the physics community. By 1942, just 3 years later, he's leading the team that builds the world's first nuclear reactor. And then another 3 years after that, he's standing in the desert at Los Alamos, witnessing the Trinity test. After they achieved that first chain reaction, this was the coded message that was sent to the project leaders. The Italian navigator has just landed in the New World, and it was so true. There, under the stands of a football stadium in Chicago, of all places, his team had built Chicago Pile 1, the very first nuclear reactor. Humanity had officially, and irreversibly, entered the nuclear age. And that hands-on, experimental genius of his, it was on display right up to the very end. Get this, at the Trinity test, as this unbelievable, terrifying shockwave is racing towards them, what's Fermi doing? He's calmly dropping little scraps of paper and just watching how far the blast wind carries them. From just that simple back-of-the-envelope experiment, he estimated the bomb's yield was about 10 kilotons. The official instruments later put it at 18.6. I mean, come on. That is an absolutely incredible feat of intuition, right in the face of this history-changing event. Okay, but Fermi's story, it doesn't just end in fire. In fact, this is where it takes a really fascinating pivot. Because those same rules he helped write for the atom, they also govern the total opposite extreme, the frontier of absolute cold. We've seen what his physics does at super high temperatures. But what happens when you go the other way? What happens when you get things as close to absolute zero as you possibly can? Well, it turns out that at those impossibly cold temperatures, you can build things with an almost perfect precision. You can literally create a ruler for electricity, but one that isn't made of metal or plastic. It's a ruler made out of the fundamental constants of nature itself. So check out this graph. It tells an amazing story all by itself. For decades, you can see our ability to measure voltage was getting better, but kind of slowly, right? But then, look at those two massive drops, like falling off a cliff, one in the early 70s, another in the mid-80s. That wasn't just an improvement, that was a full-blown revolution in precision. And that entire revolution is built on the physics of the ultra-cold. And here's what caused it: the Josephson voltage standard. This is, hands down, the most accurate way humanity knows how to measure voltage. It's what's called an intrinsic standard. That means its accuracy doesn't come from some carefully guarded metal bar locked in a vault somewhere in Paris. Nope. It comes from the fundamental constants of the universe, things that are exactly the same here, on Mars, or in another galaxy.
So how does it work? Well, the heart of this thing is called a Josephson junction. And conceptually, it's pretty simple. You just take two superconducting materials and separate them with a super thin insulating barrier. The catch? It only works when it's incredibly cold. We're talking around 4 Kelvin. That's just 4 degrees above absolute zero, the coldest anything can possibly be. Now, one of these junctions on its own doesn't actually produce much voltage. So what do? Simple. You do what you do with batteries. You link them up in a series. Engineers figured out how to put thousands and thousands of them all on a single chip, creating this long chain that builds up a stable, usable, and mind-bogglingly precise voltage.
And this is what it looks like today. This chip right here has over 20,000 of those junctions, all working in perfect harmony to create an exact 10-volt standard. And here is the punchline. This is where it all comes back to Fermi. The electrons that are flowing so perfectly in those superconductors, what are they? They're fermions. Their bizarre and wonderful behavior at these freezing temperatures, the quantum magic that makes this whole technology possible, it's all governed by the Fermi direct statistics he came up with way back in the 1920s. The exact same rules that unleash the fire of the atom also gave us the foundation for this world of icy precision, two sides of the same coin.
So when you step back, Fermi's legacy is it's this profound duality, isn't it? He's the architect of two completely different worlds, fire and ice. And yet, they're both built on the very same set of fundamental rules he helped discover. I mean, his name is literally woven into the fabric of modern science. You've got the Enrico Fermi Award, the Fermi National Accelerator Lab, Fermilab, the Fermi Gamma Ray Space Telescope. There's even an element on the periodic table named after him, fermium, element 100. His theories, his statistics, they're taught to every single physics student. The guy's impact is just everywhere. You know, Fermi once pointed out that Alessandro Volta, the guy who pioneered electricity, could never in his wildest dreams have imagined where that discovery would lead. You know, to the internet, to everything. So it leaves us with a pretty cool question to think about, right? As we keep building on these fundamental rules that Fermi helped write, what are the unimaginable technologies just waiting for us over the horizon? What's the next new world that's being built on his legacy right now?